All right, let's dive straight into this explainer where we are going to unpack the absolute ultimate cosmic biography. We're going to trace the full life cycle of the most enigmatic objects in our universe, from their violently mysterious births billions of years ago to their bizarre, almost unimaginable afterlife. Honestly, it's a story of cosmic heavyweights, mind-bending time dilation, and a totally revolutionary new understanding of physics.
So we have to start with this massive, mind-bending question. What actually happens when a black hole dies? For the longest time, we thought black holes were just these eternal traps, right? Like, once you go in, you never come out, and the black hole just sits there forever. But quantum physicists are just now figuring out that this might be completely wrong. They actually have a life cycle. And to understand how they die, well, we've got to start at the very beginning.
Section 1. The Cosmic Heavyweights. Let's meet our main characters.
Look, we've all heard of stellar black holes. They form when a star collapses, weighing maybe a few tens of times the mass of our sun, and they're just scattered throughout galaxies. But today, we're focusing on the absolute leviathans, massive black holes, or MBHs. We're talking monsters that weigh millions, sometimes literally billions of times the mass of our sun. And they aren't just floating around randomly. They anchor the very centers of most galaxies, including our own Milky Way. But how in the world did they get so big?
Which brings us to Section 2, Birth of the Giants. Let's rewind the clock 13 billion years.
So how exactly are these giants born? Well, astrophysicists theorize three distinct pathways for their formation. First, they could have formed from the remnants of pristine early stars that contained absolutely no heavy elements. Second, they might have spawned from global gas instabilities in protogalaxies driving this rapid, massive accumulation of gas. Or third, local stellar collisions in supercrowded star clusters could have merged into a ridiculously massive star that then quickly collapsed.
Now, one of those pathways creates something truly bizarre, a quasi-star. Picture this. It's a supermassive early universe system that collapses at its core to form a black hole, but it doesn't explode. Instead, it becomes this extreme cosmic cannibal. The black hole essentially eats its own surrounding gaseous cocoon from the inside out. Eventually, the whole cocoon dissipates, leaving behind this massive black hole seed right in the center of the galaxy, ready to grow.
And here is where we hit a really wild concept called cosmic downsizing. Naturally, you'd probably assume black holes are bigger today than they were in the past, right? Actually, it's the opposite. The golden era of massive quasar growth happened incredibly fast right after the universe was born. I mean, we found a record-holding quasar from when the universe was just 800 million years old, and it already weighed 2 billion solar masses. To put that in perspective, today's dominant active black holes are around 10 million solar masses. They grew up fast and they grew up early. Moving right along to Section 3, the co-evolution mystery. Okay, get this. The crucial point here is that a massive black hole almost always weighs exactly 1/1000th of its host galaxy's central bulge. Just think about how incredible that is for a second. A black hole is tiny compared to a whole galaxy, yet its mass is perfectly locked in proportion to the galaxy around it. This strongly suggests that galaxies and their massive black holes didn't just bump into each other by chance. They definitely grew up together. So we're faced with the ultimate cosmic chicken or egg scenario. Which came first? Did the galaxy regulate the black hole by, controlling its food supply of gas? Did the black hole's massive, explosive energy feedback regulate the galaxy and halt star formation? Or did they just evolve in perfect symbiosis? Astrophysicists are actively trying to solve this puzzle right now by tracking how they evolved over the Hubble time. All right, Section 4, the quantum singularity. Let's zoom all the way into the center of the hole. For a very long time, classical general relativity told us black holes were eternal bottomless pits. We believed that right at the dead center there was a singularity, a literal point where space and time just simply stop. But researchers now realize that prediction is totally unrealistic because it completely ignores quantum physics. And if there's one thing we know, it's that the universe absolutely does not like infinities. This is where physicist Carlo Rovelli comes in and completely shatters the old view. Using a theory called loop quantum gravity, researchers have made a massive breakthrough. They use this brilliant analogy of a bouncing ball to explain what actually happens inside. Just like a falling ball hits the floor, compresses, and bounces back up, collapsing matter inside a black hole reaches a maximum quantum compression, a state called a Planck star, and then it bounces back. And this is where things get genuinely mind-bending when it comes to time. Inside the hole, this bounce happens almost instantly,
in mere microseconds. But massive gravity warps time. So for us, watching from the outside, intense relativistic time dilation stretches that microsecond bounce into a multi-billion-year illusion. We think we see a frozen black hole. Actually, scratch that. It's more like we're just watching a quantum bounce happen in extreme slow motion. Which takes us to our final chapter, Section 5, the white hole bounce, the cosmic afterlife.
When the black hole finally completes its bounce, it transforms into a white hole. Now, a white hole is literally the exact mathematical time reverse image of a black hole. Space-time geometry gets so distorted that nothing can go in. Matter and information can only move outwards. And this is a real game changer because it perfectly solves the famous black hole information paradox. All that stuff swallowed by the black hole over billions of years doesn't just vanish into a singularity. It eventually bounces right out of the white hole.
Let's actually break down exactly how this tunneling transition works step by step. First, over billions of years, the black hole slowly shrinks by leaking Hawking radiation. Eventually, its external surface, the horizon, shrinks all the way down to the microscopic Planck size. Right at that exact moment, a quantum tunneling transition occurs right at the center where Einstein's equations are briefly violated, and following that, space and time emerge with a brand new structure, a white hole. When you look at the actual mathematical space-time diagrams for this, you can clearly see the flow of it all. You've got collapsing matter entering from the past, hitting that quantum transition zone right in the middle, and then exploding outward as expanding matter into the future. The math brilliantly shows us that this geometry seamlessly bridges the past black hole directly with the future white hole.
I want to leave you with one absolutely incredible, provocative thought to take away. Today, astronomers regularly detect fast radio bursts, these incredibly intense, unexplained flashes of energy hitting Earth from deep space. Well, could these flashes actually be the signals of early universe black holes finally completing their multi-billion-year bounce? Think about it. The very signals hitting our telescopes today might literally be the explosive rebirth of the oldest heavyweights in the universe. Now that, for sure, is a cosmic biography worth remembering.